I'm Jeroen van Meij and welcome to my lecture series on computer and network security. In this second video on application layer security, I will talk about how to secure web-based applications. And you may ask yourself, why do we need to secure web applications? There are several reasons for this. First of all, even if the web servers that host these applications are protected by firewalls, all web traffic, which is, for example, HTTP traffic, is considered harmless by these firewalls and they let it pass. Moreover, HTTPS provides some protection, such as confidentiality and message integrity for web applications, but it doesn't prevent other types of attacks, such as vulnerabilities in the applications themselves. And these vulnerabilities can have far-reaching security consequences. For example, it may allow an attacker to obtain sensitive information stored in a backend database that is used by the web application, or may allow attackers to actually insert new information into the websites that is then displayed to unsuspecting users and can be used to enable further attacks towards these unsuspecting users. And these vulnerabilities in web applications lead to security risks. A threat agent is an attacker that finds an attack vector to exploit a weakness in the application. This provides him with a certain degree of control over functions or assets in the application. A weakness could be a vulnerability, a known software vulnerability, or a programming error in the web application. This control may allow them to access databases, insert new information into the website, and so on. A very important source of information for web application developers about security is OWASP, which stands for the Open Web Application Security Project. It is a source of information and best practices related to developing, maintaining secure web applications. They provide trainings, talks, tools, code examples, documentation, and so on. Moreover, they always publish the top 10 of most common vulnerabilities in web applications and methods to prevent them. And let's take a closer look at the most recent top 10 web application vulnerabilities that were published by OWASP. The first one is injection. Injection, such as for example SQL injection, can be used to trick an interpreter to execute untrusted queries. This could, for example, be used to execute SQL queries that were not intended by the developers and in that way obtain sensitive information from a database or even alter the database or remove data. The second one is broken authentication. In this case, an attacker can compromise passwords, keys, or session tokens and in this way enter the system without proper authentication. Third one is exposure of sensitive data, where a web application is not properly using encryption of sensitive data that is either stored in a database or being transmitted, allowing attackers to eavesdrop on this information and steal or modify it. The fourth one is XML external entities, also referred to as XXE. This often happens with poorly configured XML processors that will execute external URIs without checking them, allowing an attacker to abuse this and access internal files of the system. Finally, broken access control occurs when the policies that restrict what authenticated users can do are not properly enforced, allowing attackers to access unauthorized resources. For example, an attacker could have a user account, but through broken access control, access functionality in the web application that only administrators should have access to. Number 6 is security misconfigurations. And this is actually the most commonly seen issue in web applications. It results from leaving, for example, default configurations or very verbose error messages that contain sensitive information. 7 is cross-site scripting, or XSS. This allows attackers to inject and execute scripts such as JavaScript in victims' browsers because of improper validation of user-supplied data. For example, an attacker could submit as part of a post on a forum some JavaScript that is then executed in the browser of any user that looks at this forum post. Number 8 is insecure deserialization, where an attacker can adjust the serialized data to perform things such as remote code execution, replay attacks, injection attacks, and so on. 9 is known vulnerabilities due to the use of old versions of libraries. Think about, for example, the Heartbleed bug that was present in OpenSSL, older OpenSSL versions, and could be exploited by attackers if the library is not updated when the vulnerability is discovered. And finally, insufficient logging makes it harder to detect and understand attacks for future prevention. This may lead to a longer detection time or even exposure to attacks. And even though OWASP publishes this top 10 and provides mitigation mechanisms, source code examples, and so on to prevent these vulnerabilities, many web applications are still vulnerable to them. A study by Veracode shows that, depending on the sector, between 58 and 76% of the websites are vulnerable to these OWASP top 10 vulnerabilities. In government websites, it's 67%, but even financial institutions, which are supposed to be very secure, have a 58% failure rate to protect against the top 10 vulnerabilities of OWASP. And let's talk in a little bit more detail about some of the top 10 vulnerabilities of OWASP. First one is SQL injection. SQL injection means that untrusted data is sent to an interpreter, in this case an SQL interpreter, as part of a valid SQL query. Under normal circumstances, a login system would work like this. The user enters their username and password into a website form, and in the backend, this information is transmitted through a post command, for example, to the backend, and in the backend, an SQL query is created using the username and the password to retrieve this information from the database and check if it's correct. Obviously, in practice, this would be a bit more complicated, as usually the password is not stored in plain text in the database, but hashed and so on. However, if the data that is entered into these text fields is not checked on the server side, the user can start adjusting these SQL queries. For example, the user could include additional information like this, and this would result in another type of query, where this part always returns true. As a consequence, this query will return all entries in the user database table, and it could, for example, be used to retrieve a list of username-password pairs, or even to log in without knowing a valid username-password combination. To make matters worse, many databases support batched SQL statements where multiple statements can be separated by a semicolon. This would allow creation of even more advanced SQL queries, such as the one displayed here, which would delete the entire users table from the database. And there are several ways to prevent SQL injection. For example, one could parameterize their SQL statements, encode and validate any input received from a form, or prevent untrusted input from being interpreted as part of a query. And here you see an example of using parameterization. In this code example, The data retrieved from the text fields in the form on the website is parameterized, and the SQL engine will actually check these parameters and ensure that they are correct and treat it literally. So any SQL statement embedded in them will not be executed. A second well-known vulnerability are XML external entities, or XXE. These usually result from poorly configured XML parsers, where the parser's desire to follow and process external DTD entities is exploited. This allows a wide range of attacks such as accessing local files, server-side request forgery, remote file inclusions, and XML DDoS attacks. Prevention is quite easy by completely disabling the use of external entities in the XML parser. At the bottom here, you can see an example of how this can be abused by including a reference to a local file, namely the file etc/passwd, which contains a list of local passwords into the XML file. The parser, if not properly configured, will just copy the contents of this file and include it into the output. You may believe that such vulnerabilities only happen to obscure websites, but this is not the case. And here I have an example of an XXE vulnerability that was present in the Google toolbar button gallery in 2014 and was discovered by some researchers. They discovered that the Google service that allows developers to create toolbar buttons for Google Chrome used XML files to store metadata about these toolbar buttons, such as, for example, styling information, title, description, and so on. When using the search functionality on this web application, the title and description of each button were printed out to the browser by the web application. The security researchers used this to create a button XML file that would print out local files with sensitive information stored on the server, such as etc/hosts or etc/passwords, when you would search for them. The source at the bottom actually provides more details about how this vulnerability was discovered and abused. The third and last type of vulnerability I would like to address is cross-site scripting, or XSS. In this type of vulnerability, the attacker will inject malicious scripts such as JavaScript in trusted web pages. It can occur in any web application that uses input from a user within the output it generates without validating or encoding it. This could, for example, be a guestbook or forum application. There are two main types of XSS attacks. The first one is a stored attack, where the injected script is permanently stored on the target server, for example in a database used for message forums or comment fields. The second one is reflected XSS attack, where the script is reflected off the server, for example in an error message or a search result, and delivered to the victim using some other way, for example as a link in an email message or through a link on another website that the user can then click. Let's take a look at how a stored XSS attack could work with an example. Let's say an attacker tries to steal a victim's identity by obtaining their session cookie. First, the attacker will use their browser to store their malicious script, JavaScript, in the database of the web application. For example, if the web application is a blog, they could post it as a comment to a blog post. They post a comment which contains the script in HTML script tags and stores it in the database. For example, the vulnerable code could look like this, where the comment is retrieved from the database and just included into the output HTML without sanitizing or checking it. The victim will then request the set of comments and receive the output from the database, where in their browser the HTML will look something like this. So as you can see here, the script is embedded into the HTML and will retrieve the user's session cookie and send it to the attacker's web server using a HTTP URL parameter. This is the last step where the victim's browser will actually perform a get on this URL, and the session cookie information will be included in that URL. And let's take a look at how a reflected XSS attack may work. Let's assume there is a web application that has an error page that handles requests for non-existing web pages that are requested from the web application. This error page may look a bit like this, where whenever a user tries to surf to the URL for a file that does not exist, it will generate output like this, not found, and then the name of that file. However, an attacker may now trick a victim into clicking this type of link, where a script is actually embedded into the URL. The web server will put this script as this information here, and it will actually execute it on the victim's browser when the victim clicks this link. This can allow an attacker to execute arbitrary JavaScript code on the victim's browser by tricking them into clicking a link. So how can we prevent XSS attacks? Well, there are different methods. For example, a web application can encode the output so that if the output contains JavaScript, it will not actually be executed on the receiver's web browser. Also, the input can be validated to ensure that when a user enters a comment or posts a forum post, no JavaScript code is present within this text. You can also use content security policies, or there are existing security frameworks to actually sanitize any data that is submitted to a web application, such as the OWASP ES API or the anti-SAMI framework. These frameworks provide several functions that allow you to encode input that is received and to validate it to ensure that it is not does not contain any illegal JavaScript, for example. As I mentioned, OWASP provides a variety of tools to help web application developers avoid having vulnerabilities in their software. A very handy tool is a Security Knowledge Framework, or SKF. It provides guidance for building and verifying secure web software. It can be used during and after development. It can help identify security lists, provide checklists, and a knowledge base with code examples on how to overcome and mitigate security issues in many different programming languages. The framework can be accessed online, and there's also a demonstration available that you can try out. And this ends my video on web application security. In the next video, I will talk about malicious software.